Okay, 3150, we're going to talk about transition state theory. This is going to be the second part of our discussion, and we're going to try to get all the way through sort of the conceptual foundation, which I'm going to briefly review because we talked about it about a week ago, all the way up to actually calculating rate constants for this simple reaction that we started looking at, the rearrangement of hydrogen cyanide. So transition state theory is a pretty beautiful conceptual framework for understanding the rates of reactions, and it's also really handy because what it allows you to do is actually calculate or estimate reaction rates without doing experiments. So in the lab, you got a handle on, actually doing chemical reactions, and as long as you have some way to measure the change in concentration of either the reactants or the products, you can actually estimate the rate of reaction. But let's say you don't have that capability and you actually want to estimate it beforehand. Okay, so transition state theory is a way that actually allows you to use basic principles and features of your atoms and molecules in the reaction to estimate those reaction rates without doing any experiments. And so one of the key concepts that we talked about already is this notion of the transition state. So why is it called transition state theory? This object called the transition state plays a key role. And so we looked at the transition state structure, which we defined mathematically as basically a first order saddle point on this potential energy surface, right? So it was a maximum in one direction, and that one direction along which it was a maximum is called the reaction coordinate, and along all other directions it's a minimum. Okay, so we'll revisit what those coordinates are for our simple system of HCN, but that's the transition state structure. The transition state itself, you can think of it as something basically like a point of no return for the chemical reaction. And it's also sometimes called a phase space bottleneck for a chemical reaction. And so this phase space bottleneck actually has a really interesting connection to other types of physical problems, many types of physical problems, but one which is kind of cool and maybe a little bit unexpected is of something like asteroid escape in sort of celestial mechanics. So imagine that you've got, okay, over here the Earth and the Moon and the Sun and the other planets. And so imagine that you're an asteroid and you're sort of stuck in this orbit around the Earth and the Sun, which are both very massive. So they're both exerting a lot of gravitational forces on you. And so let's ask the question, if you're an asteroid and you actually want to escape this orbit and move outside of the orbit of the Earth and the Sun, how do you do that? So it turns out there's actually a number of regions where the forces of gravity between all of these heavy bodies in our solar system are balanced out and sort of are minimized. And those can be really good escape points if you're an asteroid. And so then if you just think sort of intuitively, well, how should I escape? So number one, you'd imagine that if you're an asteroid taking some trajectory, that you might like to pass through those points where the forces of gravity are balanced out, so that you're neither being pulled strongly towards the sun or pulled strongly towards the Earth, because that's going to allow you to escape the orbit. But the other thing is that you might actually need some minimum amount of velocity to actually escape the orbit. Okay, so in fact, those two things turn out to be true. That number one, there's a particular coordinate region in space, just in X, Y, and Z. If you imagine sitting the Earth, the Moon, the Sun, etc., on some Cartesian coordinate. So there's actually some range of positions which are favorable for you to access. But then also you have to have some critical amount of momentum as a heavy body to actually move outside the orbit. So in classical mechanics, we call the collection of coordinates or positions and momenta of our objects basically the phase space. And so these, if you just map out the minimum, map out the favorable coordinates and momenta to allow you to escape, you'll realize that there's actually a pretty limited number of coordinates and momenta, or position and momenta, for which you can leave these orbits. So in fact, this is also, since that's limited relative to the total number of positions and momenta that an asteroid can explore, we call that a bottleneck, or a phase space bottleneck. So the same thing is true for chemical reactions. Okay, so you can imagine there's all kinds of different positions for your atoms to be in, and they can have all kinds of different amounts of energy. So they can be vibrating really fast, rotating really fast, translating really fast. But there's only a very particular way in which you can actually get your atoms to traverse your reaction coordinate in such a way that they make their way from reactants to products. And so again, there's a very limited region of space of both positions of your atoms in the energy or velocity of those atoms, or momentum, however you want to think about it, that allows you to traverse from reactants to products. So again, we actually think of these things as being bottlenecks. And in fact, what we call the transition state is defined also as a very special bottleneck that separates reactants from products. So anyway, so that's an interesting and very deep picture that's been exploited really extensively in physical chemistry throughout the years. So it's kind of important to have, a little bit of an appreciation for that. Okay, so let's remind ourselves that we're talking about this chemical reaction. So we have HCN, and we're going to go from HCN to CNH, which means we're going to just rearrange this molecule. Okay, and so we talked already about this. We can think of about 3 different coordinates, unique coordinates for this atom, right? We've got basically bond length between carbon and nitrogen. We can think about a bond length between carbon and hydrogen as well, but in fact we're going to do something slightly different. We're actually going to define a length between hydrogen and the center of mass of carbon-nitrogen, and we're going to do that for a particular reason. So we'll call that big R, that distance. The carbon-nitrogen bond length we'll call little r. And then there's also this gamma angle, which is basically the bond angle. And the gamma angle you can see for this migration of the hydrogen atom is really the key coordinate that we have to move along to go from reactants to products. So we call that our reaction coordinate. Okay, and so this region in our space, which separates our reactants from our products, this is called the transition state. And so this is basically our bottleneck region that separates the reactants from the products. Now, there is one special structure of the molecule at the very apex of this potential energy surface, at the very peak of this potential energy surface along gamma, which is also a minimum along all other coordinates, and that's called the transition state structure. So this has a very special sort of geometry, which is called a first order saddle point. And so in fact that's basically what we use to define the transition state structure. Okay. So in the language of transition state theory, basically we're going to talk about 3 distinct structures: the reactants, the transition state, and the products. And so in this case, the reactants are called hydrogen cyanide, and so concentration of reactants is equivalent to concentration of hydrogen cyanide. The transition state is basically hydrogen cyanide in this critical geometry, which we denote with a double dagger. So the transition state concentration is going to be equal to the concentration of hydrogen cyanide in this critical geometry. And then the products are an actual new molecule, an isomer, right, of C and H. So the products concentration will be equal to the concentration of C and H. And so the notion of transition state theory is that we can have this equilibrium between hydrogen cyanide reactants and the transition state activated hydrogen cyanide. And basically we have a forward rate, which we'll call K1, a backwards rate, which we'll call K-1. So forwards rate gets us from reactants to the peak of the potential energy surface. K-1 gets us back down. And the balance of the two we can equate to the equilibrium constant. But then there's this other rate, K2, which is the rate at which transition state goes to products. Okay, and so the first step is reversible. So transition state can go to products or back to reactants, but we assume that once we're products, we will not go back to transition state. Okay, so crossing the transition state is the point of no return. Remember, that's why we say we assume we can't go back, even though, of course, in reality, we know that these things can be reversible, but we need to make this assumption for transition state theory. Okay, so what's the whole goal here? So the goal is actually to provide us a way to talk about the rates of the reaction, basically how fast does this reaction happen. And so this is a pretty simple reaction, right? It's called unimolecular, just involves one molecular species, just one molecule rearranging to form a new one. So we can basically say that the rate of consumption of reactants, basically negative d r dt, is equal to the rate of formation of products, dp dt, and all of this is equal to basically these two constants times reactant concentration as a function of time. Okay, and so this part of the constant here, k double dagger, that's the equilibrium constant for the transition state relative to the reactant products, and then the second k actually is mislabeled. It should be this k2 here. Okay, so basically a product of this k2 with the equilibrium constant is what will define our transition state theory rate constant. And the really amazing thing is that we can use information about the molecules themselves to estimate that rate constant, and that's what we're going to talk about. Okay. Now, one other thing I'll say is that this is what's called a differential equation. So it tells you about the rate of consumption or the rate of formation of your reactants with respect to time. And it's a very simple differential equation. It tells you that, you know, if you look at how the reactants are being consumed in time, for example, at any given time, the slope is just some constant multiplied by the instantaneous concentration of the reactants. Okay, so even if you've never seen this differential, well, so first of all, you've probably seen this differential equation before, even if you don't recognize it. But in essence, what we seek to do here is actually find this function that describes the reactant concentration as a function of time, so that in any instant in time, we can know what the reactant concentration is. And so in fact, we basically are looking for a function where if we take its derivative, we're going to find that what we get back is the function itself multiplied by a constant. Okay, and so the function that satisfies that criteria is basically the exponential function. So e, the natural number e raised to the negative constant times t multiplied by some initial concentration of reactants turns out to be the general function of our reactant concentration as a function of time. Okay. And then similarly, because we know the relationship between reactants and products is 1-to-1 by our stoichiometry, we can say that basically the product concentration as a function of time is nothing more than the initial reactant concentration minus the amount of reactants that have been consumed. And so this can be rewritten also in terms of the initial reactant concentration. So it's just initial reactant concentration multiplied by 1 minus this exponential. Okay, and the important thing is that we can control the reactant concentration, right? That's something that is within our ability to control in the laboratory. Okay, so in essence, if we know how to calculate our rate constant, then we can basically know what our reaction is going to be at any instant in time, provided we can at least specify how much reactants we're going to have. And so here's basically, if you want to plot what those functions look like as a function of time, I've plotted these in basically a reduced coordinate system. So on the y-axis, I have basically concentration divided by initial concentration. So of course, no matter what the initial concentration is, that basically instantaneous concentration divided by initial concentration will always be 1 at the beginning of the reaction, just by definition. So make sure you can convince yourself of that. And then how does the relative concentration change as a function of time? It's going to drop off exponentially. How will the product concentration look like at the beginning of the reaction? Well, of course, it has to be 0. But if the reactants are basically being consumed exponentially, then what I'm going to see is this basically converse growth, which is going to rise exponentially and then sort of asymptote off to the amount which is equal to essentially the initial reactant concentration. Okay, and so couple of one other interesting thing that you can think about is along this axis, and so let me also say that the time axis I'm using is a little bit arbitrary as well. This isn't seconds. This is actually time in seconds divided by the total rate constant. And so the total rate constant is going to be in inverse seconds. So basically, I'm getting a dimensionless time when I do these two things. Okay, when I take time divided by the rate constant. Okay, and so the other thing you can look at is, well, at what time are half of the reactants consumed? Okay, and so that would be called like the half-life of this reaction. Okay, so that's this point on the graph right here where the purple curve and the green curve meet. That would be at the half-life of the reaction. Okay, so how do we actually calculate this equilibrium constant? Well, we're going to use some result from a branch of physical chemistry which we have not really explored yet, which we should have, but or would have been nice to have, but we just don't have time in Phys Chem 1 to really get too into statistical mechanics. But anyway, the notion is that you can write the equilibrium constant using sort of the microscopic information about your molecules as contained in these quantities called partition functions. And these are what are denoted with the Q here. So Q underscore TS is the partition function for the transition state. Q underscore R is the partition function for the reactants. And so basically taking the partition function of the transition state and dividing it by the partition function of the reactants and scaling it by this exponential where we take the total energy difference between the transition state and the reactants divided by Boltzmann's constant times temperature. That is the definition of the equilibrium constant that describes the equilibrium between the transition state and the reactants. Okay, so you can see that this equilibrium constant, of course, has got to depend upon temperature because of this term here, but it turns out that the partition functions also depend on temperature. So just very briefly, what the partition functions do is basically they spell out all the different ways that you can put energy into your system. So they enumerate these energetic degrees of freedom, and they assign weights to those energetic degrees of freedom that depend upon temperature. So even though we haven't explored these partition functions yet, I want you to think back to when we discussed the heat capacity as a function of temperature. And one of the things that we discussed was that the reason why the heat capacity of a molecule depends upon temperature is because as you go to higher and higher temperatures, more energetic degrees of freedom become accessible. So that means you can put energy into those degrees of freedom as you increase the temperature. And the more different ways you can put energy into the different degrees of freedom, the smaller the observed change in temperature will be, because the observed temperature is all about putting energy specifically into your translational degrees of freedom. So at very, very cold temperatures, essentially I can access only transitional degrees of freedom of my atoms and molecules. But as I start to raise the temperature of, let's say, a diatomic molecule, all of a sudden I can start to put energy also into rotations. And that gives me an additional degree of freedom for putting energy in, which means that less energy will be dumped into translations, right? Because I now have a choice to put into translations or rotations. If I keep going up, I can access vibrations as well. So the same idea here is true. In fact, the partition function essentially just quantifies the probability, or helps you to quantify the probability of putting energy into a particular degree of freedom of your molecule as a function of temperature. And so what can we say about how to calculate the partition function just in general? Well, it's essentially going to be, so number one, what we're going to do is we're going to make the assumption that the vibrational degrees of freedom of our molecule are the most important. So let me just skip back slides a few and mention that the vibrational degrees of freedom that we'll be talking about for our molecule are going to include the stretching of this H to center of mass distance, which we call R, the stretching of our CN distance, which we call little r, and the bending of this HCN bond, which we call gamma. Okay, so then essentially what we're going to do is we're going to assume that those three types of vibrations are the only ways that we can put energy into our molecule. And of course, that's an approximation. It neglects other ways that are possible, like translations and rotations, and even the electronic motion of the molecule. But within that assumption, essentially what the partition function is a product. This pi notation is for product among all of the distinct vibrational degrees of freedom. So, and then each vibrational degree of freedom is a sum over all possible vibrational energy states divided by Boltzmann's constant times temperature. Okay. So we're going to see that this actually reduces to something which you can compute pretty readily, but this is formally how you would express the vibrational partition function for our molecules. So this J, by the way, just counts the different degrees of freedom. So J would basically list out little r for the CN vibrational mode, big R for the H to center of mass vibrational mode, and gamma for the bending mode. And N would count up all of the different vibrational energies for each particular mode. Right, so this is just a little movie of vibrational modes, not of our HCN molecule, but of our favorite molecule, triatomic molecule, water. So I just want to remind you that, in fact, these vibrational energies you can actually measure in the lab, or many of them you can measure in the lab. Not all can you measure in the lab necessarily, but that doesn't mean that they don't exist. Anyway, that's I don't want to kind of go down this road of like what is IR allowed and what's not IR allowed. But if you have IR allowed vibrational modes, you can measure their energy in the lab by doing an IR spectroscopy experiment. Okay. So I mentioned that it will basically take the vibrational partition function as a sum, basically a product of sums, and the sum is going to go over all possible vibrational energies. So this is something which is giving us a little bit of a preview to something we'll talk about in detail in Chem 3160, which is about like quantum mechanical picture of vibrational motion. In essence, what I really want to convey to you is that each one of those vibrational degrees of freedom for our HCN molecule, we can calculate its frequency if we know the following two things. Number one, we need to know the masses involved in the vibration. So we essentially have a systematic way of defining the masses involved, and we'll calculate something called the reduced mass. And we'll see how to do that again in Chemistry 3160. So this is still a bit of a preview. And then we also need to know essentially the stiffness of the interaction that either defines the bond, like the bond stretch, or the bond bend. Okay. So knowing those two things, you can calculate the vibrational frequency. And so this is basically making use of what's called the harmonic oscillator model. And we'll talk about that extensively. Okay, so once you have that frequency of a given vibrational mode, the energy is actually nothing more than Planck's constant times that frequency. And so this is essentially a way of expressing any possible energy of vibration for your molecule. So those vibration that sum over n different vibrational levels that we saw earlier, n is basically an integer which starts at the number 0 and goes up to infinity. So that's an infinite sum uh, that goes from 0 to infinity. However, there's actually a way to deal with that infinite sum, which has been worked out up here. And so essentially all we really need to know is for each degree of freedom, we don't need to know the energy of every possible vibrational level. We just need to know this one fundamental frequency, which depends on the stiffness of the interaction and the masses involved. And essentially each individual contribution to the vibrational partition function has this following form here. So we can write Q sub big R for the contribution which depends on the hydrogen center of mass distance. We can write Q sub little r for the part that depends on the Cn stretch. And we can write Q sub gamma for the term that depends on this bond angle. And then essentially what we need to know for each one is what is the frequency of that vibration. Okay. So moving along, what I'm going to do is essentially make one more simplifying assumption, just to save, basically paper for everybody who's going to actually compute these things. And so what I'm going to do is I'm going to assume further that this bond, this distance between hydrogen and the center of mass, is not important. So it does not contribute to the partition function. So that means in essence what we need to do is we need to calculate the partition function for the Cn bond length, which we'll call Q sub r, and the partition function for the bend, which we'll call Q sub gamma for the reactants. And so this will be the partition function for the reactant, which is in the denominator of my equilibrium constant expression. So essentially what you should do then is use this data that I've given you, which is that the frequency of the Cn stretch is this number. So this basically 1.3 times 10 to the 14 hertz is the frequency of this Cn stretch. And then the frequency of this bending vibration is basically 6.8 times 10 to the 13 hertz. Okay. So in essence, once you have that information, you can go ahead and calculate the partition function for the reactants, provided that you know the temperature. And you'll see at the very last slide, I'm going to tell you to do this, and I'm going to tell you that the temperature is 300 Kelvin. Okay, so now for the transition state, how do we define the partition function for the transition state? Well, in fact, what we're going to do is we're going to assume that that the gamma mode is no longer important for the transition state partition function. It makes no contribution. It enters into the picture in a slightly different way, which we'll see in a minute. So if that means that the gamma mode is not important and the big R mode is not important, then the partition function for the transition state is going to only depend upon the partition function that accounts for the little r mode, the Cn stretch mode. And again, we're going to have a frequency for that Cn stretch. It's 1.3 times 10 to the 14 hertz. So you can see that in essence, we're finding that the Cn stretch frequency doesn't change when the molecule is in the transition state structure compared to what it is when it's in its reactant geometry. Now, will that always be the case? No, that will not always be the case. So your geometry is definitely different in the transition state. So in general, you might expect that the vibrational frequencies of your molecule will be different when it's in its transition state geometry compared to when it's in its reactant geometry. But in this particular case, we're finding that the frequency does not change. Okay, now finally, we have to deal with this gamma mode. So we said it doesn't enter into the partition function, but nevertheless, once we're in this transition state geometry, we still have motion along this gamma coordinate. And in fact, it's that motion along the gamma coordinate which is going to take us over the hill down to the products. So in fact, the frequency of this gamma mode when you're in the transition state plays a critical role in the overall rate of the reaction. And in fact, it is that frequency is actually what defines the rate constant, which we discussed in the very first slides, which we called K2. The rate constant for going from transition states to products is actually equal to the frequency of the reactive mode when you're in the transition state structure. Now, is that strictly speaking true? No. This is an assumption of transition state theory. And in fact, if you look through the transition state theory literature, which is quite extensive, you'll see many different ways of treating this, this equivalence. You may see that this frequency has been scaled by some number, and that number may be sort of empirical, meaning that someone might just adjust it as needed, or they may have ways of calculating a scaling factor. But nevertheless, the fundamental idea is that K2 is related to the frequency of the reactive mode in the transition state. And this is a good time to just pause for a minute and ask yourself if this dimensionally makes sense. Should K2 have dimensions of inverse time just like the frequency does? Think about that and go back to your rate expression and see if that's true. And one other hint that I'll give you is that in fact the equilibrium constant, big K double dagger, should be a dimensionless quantity. So go back and think about that if it's not obvious to you. So in this case, we just need to know the frequency of the reactive mode in the transition state geometry to know K2. And here is the frequency of the reactive mode in the transition state geometry, 3.4 times 10 to the 13 hertz. And you can see this is about half what the frequency of the gamma mode was in the reactive geometry. So that's not entirely uncommon for the frequency to be lower of the reactive mode in the transition state compared to in the reactant geometry, because essentially what we've done is we've sort of loosened up the interactions because we're on the precipice of breaking bonds and converting into a new product. Okay, so here's your task now, is to take the information from these slides and actually go ahead and compute the rate constant for this rearrangement and compute the half-life of the rearrangement, meaning don't just find the rate constant, but also figure out how much time it takes in seconds to go from some initial concentration, which you might as well just say is 1 molar, and go to half that concentration, which would be 1/2 molar. Okay, so you have everything that you need to calculate all of those things. You need also the total energy difference between the transition state and the reactants. I'll remind you from this relationship right here. Okay, we didn't discuss that yet, what that energy difference is, but I'm giving it to you right here. The energy difference is 3.1 times 10 to the minus 19 joules, and you can assume this reaction is happening at 300 Kelvin. So there it is. I hope that was interesting and informative, and we will discuss the solution in class.